in normal media, you would expect a small energy loss over great distances because of the interaction of the wave with the medium. So photon waves would get redshifted a little bit, in theory, over great distances, which would then explain the redshift without actually expansion. So in this model, it basically means there is no expansion of the universe. The redshift is actually caused probably by a very, very small, tiny energy loss over great distances. So, and we know how this works mechanically in normal elastic solids. So if we could use that research there and do some experiments to detect that somehow in a lab, I don't know if that's possible.
It would be interesting to see if the Hubble constant is actually giving us insight into a property of the medium.
Exactly.
I'm very pleased to present to you Chantal Roth. Chantal has her PhD in scientific computing and her master's in biochemistry. She works in the biotech industry, mostly developing algorithms. But in parallel, she's an independent researcher whose goal is to identify the underlying nature of the ether. She has her own model, which she's going to present to us today, which is an integration of the work of many physicists that she collaborates with. I have personally found her model of the ether to be the most compelling model I have seen so far, so I'm very excited to let her give her presentation for you today. Chantal, thank you very much for coming on Inductica. Why don't we get right to it? Show me what you got.
Let's dive in. So I'm going to share my screen. So basically, I want to talk about the mechanical universe. And the idea is I want to build this from the ground up. So the question is, how can we build basically all of mechanics, all of quantum mechanics, relativity, using an elastic solid model, okay? So, and please interrupt me anytime, okay? So first, I want to briefly talk about the motivation, like why in the world do we want to do this? And then we're going to dive into, and of course, I can't cover everything in great detail. So I want to just try to cover a lot of ground, but not go into the depth as much, right?
Now, right up front, I want to ask, I would like to just give our audience right up front a broad overview in 2 sentences or so. What are you trying to achieve with your research?
Oh, I have a slide on that, okay? Like 2 slides.
Okay, great.
2 slides.
Great.
2 slides.
Fantastic.
So just an overview. So basically, I'm going to go over general relativity real quick, okay? Special relativity, Maxwell's equations, spin 1/2, and maybe charge, depending on how much time I have. So the motivation is, I always, even as a child, I asked the question, how does a magnet work exactly? And nobody could tell me. Sure, there are formulas and everything, but nobody could tell me, mechanically how it works. Same thing about relativity, why is C constant? I want to know why, not just it is, right? I want to know why exactly. Is there a logical, simple explanation for that? And also, spin 1/2, what is it, right? And of course, it gets even worse with quantum mechanics, right? Because, there's all these interpretations, from many worlds to pilot wave and hidden variable. None of them explain anything. The pilot wave kind of, sort of, but even there, what's that wave? Why is there still a particle on top? And it just bothered me. And so I want to really find out how this all works. So basically, there are all these things in physics, all these puzzle pieces, from Schrödinger to Dirac, the Maxwell equations, they all have to fit together somehow. And I think one of the problems is people, they dive into one tiny aspect. Like there's people who spend their whole life in a one tiny aspect, but they never see the full picture. So what I want to do is to find, based on all the research out there, is there something that kind of makes sense overall? And, you ask me why. So, of course, the mainstream has a lot of explanations, right? And the math is all fine. We know how relativity works, the mathematics of it. We know how quantum mechanics works, the mathematics of it. We understand Sabine in terms of mathematics, but it doesn't explain anything. There's no, people say, shut up and calculate, right? And I want to know how it works. So, and to me, the idea that there's just a vacuum and there's nothing doesn't explain any of this, right? So the math is fine, but I want to understand how it works. And reading from all these different possibilities, it seems to me the elastic solid approach is able to explain all these things in a really simple way. That's what I like about it, from the ground up. And, literally easy in a way that even a elementary school kid could probably understand, at least to some extent, right? So that is basically what I'm trying to do. And and if you want to, I can go ahead and just go dive right into the next topic.
That answers my questions. So what I was going to ask you is, first, a broad overview, which you've given us, which I've taken as like, the way to put it in my language, you think there's an ether, and an ether actually explains things. Is that yes. A word you yourself would agree with? Is an ether?
Totally. The only hesitation is people have been using that word, meaning all kinds of different things, from like gas type thing to fluid. So sometimes there's just confusion about this, right?
I'm going to ask you about some views related to that. Like, what exactly is the ether? I'm going to ask you about that later once we see your hypothesis that you're putting together. And then the other question I was going to ask, which you've basically answered, is what's wrong with the existing line of research? What's wrong with the existing set of premises?
Exactly.
And you've answered that as well, which is that it doesn't explain the actual things going on.
And there's a lot of weird stuff, like all these paradoxes.
Right, to say nothing of the fact that there are things that just can't be true.
A photon, wave, or particle. You shouldn't have these weird contradictions. To me, that tells me something is missing or wrong. Speed 1/2, there's no explanation of what this is supposed to be. Matter and antimatter, it's kind of weird. Like, why would they annihilate if they're particles? There's no real explanation, right? And so a wave model can answer a lot of these questions really in a simple ways. And it doesn't take much. The only thing we have to postulate, really, is that whether you want to call it vacuum or space is not empty. So there is something which is very simple. It's just an isomorphic, elastic solid. And that's it. And everything else you can derive from that, basically. And now usually it sounds
real quick,
weird.
what does isomorphic mean?
Well, it's just, it's homogeneous. It's the same everywhere. It's ideal. So, it doesn't break. It's just like a perfect elastic solid, basically.
Okay.
It's, the same in all directions. And and of course, I don't know if it's granular or not. Like some people have idea that there must be a smallest element in there, but I don't think we can tell that yet, right? Maybe we'll find out eventually.
I agree.
It could be continuous or not. I wouldn't know. I just know it would make sense from the mathematical perspective. Both right now are feasible because we don't have experiments to distinguish the two, as long as it's some kind of elastic solid, basically.
Yep.
So, I just go to the next topic, general relativity. So don't worry, I won't go much. I don't have time to go into all the details. But so just basically, from a historical point of view, even Einstein said that the space must be real and actually rigid. He said even himself that special relativity does not compel us to deny ether, and he even said that according to the general relativity, space is endowed with physical qualities. So in this sense, therefore, there exists ether. He even went as far as saying space without ether is unthinkable. So I'm always surprised when people just say, no, Einstein proved there's nothing there, right? Well, that's not what he showed, you don't need it in the math, you don't need it. But, he even himself said he thinks there should be something, right? And what I find also interesting is, let me just go to the next slide. So people actually use Einstein's field equations in optics. Okay, so there's the notion of an optical black hole. What this is, and there's a bunch of papers on this, is basically you have an optical medium, like glass, something like, and you have a varying refractive index. So your refractive index gets larger and larger as you go towards the center. And this makes the light waves to go spiral around. And you can even basically create a optical black hole that way. And it's using the same equations as general relativity, which is really interesting, right? Same equations, okay? It's just one of the clues. Like when you think about this whole puzzle, there are all these clues here and there which make you think, And then funny thing is, and I just learned this like 2 months ago or something, that even Newton, he postulated that space must be a medium. And it's kind of old language, but he says, like, doth not the refraction of light proceed from the different density of this ethereal medium in different places? The light receding always from the rarer parts of the medium, right? And it's not the density there, and so on. It's kind of funny how you wrote it, right?
Those words are burned into my memory from the queries, incidentally. I'm glad you too have memorized them, or nearly so.
And then, also he talks about, and though this decrease in density may at great distances be exceedingly slow, yet is the elastic force, funny how it's spelled, right? Elastic. The elastic force of this medium be exceeding great, and so on and so on. So another clue, like Newton was pretty smart, right? And he even thought of this, is there a way to explain this whole thing, gravity, using some kind of refraction model, refractive index, using some kind of medium that has density, right? And luckily, there's this really smart guy called Hagen Kleinert. I think like in the 80s or 90s or something, he mathematically has proven or shown the equivalence of the Minkowski space-time to a model where you have Euclidean and Euclidean three-dimensional elastic solid with varying density. So you can imagine like a big pudding sitting on your table, right? Of course, he calls it crystal, but it doesn't have to be crystal, okay? It's just, I guess it sounds cool, word crystal. It could be some kind of like a jello-like thing, but it's based on the properties. It's got to be really stiff, okay? Because you're going to have to get the speed of light, right? It's got to be really stiff. So he has shown that you can map this. It's just a coordinate transformation. And so instead of having this really kind of hard to imagine four-dimensional Minkowski space-time, which is, I don't know if you can picture it, right? You have just a regular three-dimensional universe. There is a fourth dimension, and the fourth one is really density, right? So the density is not the same everywhere, basically. Where you have a lot of matter, a lot of stuff going on, it's denser. And so this leads to a change in refraction, or refractive index. And now if you think about that everything is composed of waves, so matter and light, and waves bend, they get, due to the refractive index, they bend, you get general relativity and gravity out of this.
Yeah. So let me quickly summarize that, and you can tell me if I'm understanding it properly. So the idea is that there's a medium, there's an ether, and massive objects such as the Earth or the Sun will make the ether denser in their locale. And since light waves are waves in this ether, this creates a different refractive index in different parts of the ether. And just to review what a refractive index is, that's crudely speaking, it's on the first level of analysis, it's the speed of light in different media.
Yeah.
So light goes a different speed in light goes slower in water than it does in air, and this is what causes light to change directions when it goes from water to air, and that's why a fish isn't at the location.
Yeah, exactly. Yeah, that's a good example. When you wear glasses, everyone who wears glasses uses that, right? So.
Right, and if you look through your glasses at like a weird angle, then it gets distorted. That's because the light's changing directions as it goes through your glasses.
Yeah, and let me just enlarge this. You can actually do this experiment even in your kitchen. So you take a bowl of glass. It has to be, I guess the walls have to be kind of flat. You add water and sugar, lots of sugar, okay?
Oh, hang on. Before we move on to to this part, I just wanted to finish that thought on gravity.
Oh, sure, yeah.
So the idea is that the ether medium gets denser near, the Earth or the Sun, and that causes the light to bend in the same way that it bends as it passes from glass to air. And as you were saying, Newton had this same hypothesis.
Yeah.
And this difference in density must somehow also be responsible for the gravitational force.
Yeah, exactly.
So as you say, I'm really seeing it. The pieces start to fit together. Anyway, just wanted to summarize that. Let's tell us about this experiment now.
You take a bowl of water, you put sugar in it. Don't stir much. So there's a gradient of sugar. So you have more sugar at the bottom than at the top. And then when you shine a laser through it, so there's now a gradient of refraction. So the refractive index increases as you go towards the bottom, and light will bend. And that's pretty cool, right? I mean, this is so simple, right? And so if you imagine the universe is something similar, and because matter is also wave, so matter will have the same, it will be bent the same way, basically. So matter will get attracted towards a denser area the same way. And so basically, if you look, I'm not going to go more into formulas, but just, when you look at the metric tensor from general relativity, right, it basically contains the gravitational constant and the mass, basically telling you how the Minkowski spacetime is curved at that spot, right? Similarly, we replace this by a density function. It's really, to be more specific, it's a plastic gauge field. But anyway, it's related to density, so the density will tell us how much curvature you have, basically, at a particular place in the universe.
And is this density, is it a function of, it's a function of R, three-dimensional position, not just
Yeah, exactly.
S, right?
There's also other terms in it, so it's not just density alone, but also the twist, the strain, it has multiple parts, right? It's not just density alone.
So this density, is it actually a tensor?
Yeah, it's a tensor. Yes, exactly. Because yeah.
So I mean, is it analogous to the metric tensor, or
it's analogous to the metric tensor, but it contains the density is in there, right? So the density of the medium is in there, basically. But you might also have twists, right? Different kinds of strains. Yeah. So that's about as far as I will go with general relativity.
Right, yeah.
If that's okay, because otherwise I have like 60 slides, okay? So,
right.
Let's see, where am I? Okay, so if that's okay, I'll go on to the next puzzle piece, that's special relativity. Yeah. So I think we covered that part. The question is, well, how do we explain special relativity, right? Another important piece. So, of course, and basically what I want to show is that special relativity is an emergent phenomenon of any wave-based system. Any system that's composed purely of waves will have the same, outcome, the same mathematics, and it's so simple. I really swear, even a first grader would understand. The only thing you have to know is that the speed of a wave is normally constant in a medium, assuming same pressure, same density. If we keep the density the same. There's a wave speed in water, for instance, right? There's the speed of sound has a certain velocity, assuming same pressure and all that. So, in diamond you have a wave speed. Like in diamond is pretty stiff, right? So in diamond you have really large speed of wave. So it's like 12,000 meters per second. That's pretty large. Now, of course, in our case. The speed of light is much larger even, right? So the question is, what kind of properties would that medium need to have for it to have such a large wave speed? And basically, the speed of the wave can be derived from the bulk modulus of the medium. Has to do with the stiffness and the density of the medium, right? So you can have either it's got to be super, super stiff, so like much stiffer than diamond. I guess that's why Hagenklein called it a crystal, because it's kind of it's very stiff. Or it could have very low density, and of course we don't know the numbers, we don't know the values. But just to picture in your mind, right? It's got to be something really, really stiff, at kind of low density to picture this kind of this medium.
Yeah, one argument that's been given against the ether, I don't think this is a good argument, is that the stiffness has to be many, 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 many times more than the density. And from what we're accustomed to, you need a certain density to make stiffness, to make something very stiff. Like, so if you think of air, like, it's very rare, it's not dense. But the stiffness isn't that high as a result. So and that's an argument against the ether, is that it would have to be a substance unlike any other we have seen so far.
Oh, it would be, because it won't be a substance that we know, right? Because it's like Einstein, it's not a normal ponderable matter. It's beyond our, we can never see it from the outside. We are inside. We are like these wave beings in this pudding, right? We can never see it, unfortunately, which is kind of sad. But we can only deduct the properties using our language. So,
But I mean, a lot. We've been far past the level of which we can see for centuries now. We can't see atoms. Actually, it was only recently that we kind of could. But it's still like we can image them, but it's not. That's not the same thing as literally laying eyes upon them, which we never have and never will.
Yeah. And so what's important here, though, right, when we talk about special relativity, often people say, well, the speed of light is independent of the reference frame. And the thing is, it turns out that way when you calculate it. But here we are saying there's an absolute medium. In that absolute medium, the speed of light is constant, okay? Which people will go, oh, no, that's not constant. Well, it will turn out to be, like we as observers inside, we always see the same speed of light, even though in an absolute sense, it's actually constant in the absolute sense. So that's the only really distinction we have to make between the mainstream model, which says it's constant, but there's no absolute speed. And here we are saying there is an absolute speed. So like we are like gods outside of the universe and watching this, and we're looking at this, and we are saying the speed of light is constant, right? And then we'll see what happens. So to make this easy, this is a very simple analogy, okay? And of course, I'm going to go from the boat to the actual elastic solid afterwards, but I think this helps to really understand. It's a very, very simple concept. So all you have to know, the speed of a wave is constant. So like a water wave. So here we have a water clock. It's very simple. So we have like this boat. There's a bell here. There is something like a stick or rock that you drop in the water, right? And then the wave spreads in all directions. And we call the water clock, it makes one tick when the waves start to hit the bell. That's what we call one tick. So we throw the rock in the water here, and after, let's say this takes 4, like we are outside of the universe, right? So we have our godly clocks, constant clock.
We're outside the water. We have a clock.
We are outside the water.
Runs
Like
by
we
a
watch
different
it from
standard.
outside of the universe. We have our own clocks, our absolute clocks. We say, well, this one tick is 4 seconds, for instance. So it takes 4 seconds for this wave, to reach the bell. Okay, very simple. And now what happens when the boat is moving? So before, it took us 4 seconds, right? Now, when the boat is moving, remember that the rock went in the water here when the boat started to move. The boat is moving to the right. So as the wave is spreading, right? Well, the boat has now moved. After those 4 seconds, the boat is no longer here, right? It's moved to the right. So now, as you can see, the wave has to travel a longer distance to reach the bell. So now that one tick is no longer 4 seconds, but maybe 6 seconds. Do you see that?
Yes, I see it. Sorry, I muted myself and started writing down a question for you for later. But yes, this makes perfect sense.
Totally trivial, like literally, like.
Yeah, it's just and this is. Yeah, well, I won't steal your thunder. Yeah, go on. Yeah.
Yeah, it's okay. So it's really, I make this really simple just on purpose, because people always say, oh my God, special relativity is so difficult. It's really not, okay? So now we have to
it doesn't have to be.
It's just, it's literally distance times time times speed. So, let's say we want to figure out how long it took for the moving boat. If we know it's 4 seconds for when it's standing still, right? We have 4 seconds times the wave speed c, while at that time, the boat moves at velocity v, and so we have the triangle, and guess what? You get the Lorentz factor out of this. If you just do the very simple math, the triangle x v squared plus this square equals the hypotenuse squared. You get the Lorentz factor. That's it. I mean, that's all it is. It's literally that simple. And similarly, you could also get a length contraction, because what happens is, what is a measuring stick? A measuring stick is composed of waves too. When you zoom in, right, it's composed of waves. So, and a moving wave, if you imagine you have you drop a rock in water, and it makes these circular waves. When you do this in a river, right, the one side, the waves get bunched up, right, from the Doppler effect. So your waves are compressed. That means a moving stick gets compressed. So you get the length contraction just the same way. And of course, we are in our case, we are not in a water or a boat. We are all composed of waves. So basically, when we say that light is composed of waves, and matter is composed of waves, then you automatically get special relativity. That's it. It's that simple. So, like in our case, we are composed of waves, and of course we're not in the water, but we are in this elastic solid. It's the same thing. It's literally the same thing. So you can imagine there's something called phonons, which is sometimes called particle of heat. So in a body, you get these quasi-particles that are modeled like photons, but they're called phonons. Same thing, So we can do the same thing now in the elastic solid, and we get exactly the same thing. So it's super, I think, simple. And obviously, there's lots of publications out there. Also, Robbert, by the way, he has done a lot of work in this, and I'll share the link. He has done some animations of this as well. He has also written a lot of papers on this to explain with animations how this works exactly the same way. Yeah, okay. So, and so I guess if it's okay, we can move on to the next topic.
Let me make my own comment here real quick. My way of understanding this very quickly is that entities, or let's say this: bodies as we're aware of them, like matter, objects made of matter, are perhaps made of these ether waves. And when they travel through the ether, they're made of these ether waves, and changes within these entities, these bodies, are always some kind of ether wave going back and forth. And for that reason, the same delay in time that applies to this water clock you've shown us, or the Einstein light clock, as it's known in the common literature, those same delays apply to the ether waves, which is why, quote-unquote, time dilates. But it's not time dilating. It's simply the duration of processes of change.
Yeah, exactly. I'm glad you brought this up. Because even if you have, let's say you have an atomic clock. What is an atomic clock? It's a vibration of some atoms, right? So we think
it probably is something like that.
Or like a wave going in a circle,
ultimately, we don't know exactly what's that.
So even let's say a clock is a wave going in circles. When you move that wave, it's now going in a helical path. It has to travel longer distances, so it will take it longer. So basically, this is saying there is an absolute time, I guess, outside the universe, but we never know it, right? All we can do, we always measure our time inside that elastic solid.
Well, that's going to be a question I have for you later, because I don't think there's any evidence of an absolute time, but we'll get to that if we have time.
It's just because we are kind of watching from the outside, like we are pretending right now there is, of course there isn't probably, but you know what I mean?
Right, it seems like that seems to me like a problem, like we need to modify our description, because currently, as you're saying, your description is in terms of some godlike standard. And if there isn't any such standard, that doesn't mean we're wrong. That doesn't mean this isn't onto something, but I think maybe the description should be changed, since there is no there's no evidence of any such outside the universe godlike duration.
Yeah. The thing is, when you calculate this, it all cancels out. So you don't need, that's what Einstein was saying, right? You don't need an ether in terms of math. This all cancels out. All you end up with is the relative measures, right? And so it all cancels out. So that's why I guess he was saying we don't need an ether. We don't need anything in the math. Like similar when you have the Doppler effect you don't need the error to explain the Doppler effect. Although mechanically you need it, but for measuring or calculations you don't need it anymore, right?
You could just blindly apply the formula and forget the fact that air exists that actually carries.
You don't need it, right? The formula air doesn't come up, right? So it's just initially.
Well, you need it, but you don't need it to make specific kinds of predictions.
Exactly. Similar here.
You will need it to make further predictions, though.
Yeah. Exactly. Yeah. So let's again change topics completely.
Yeah, well, this is the nature of it. If this is jarring for some people to keep switching topics, you got to remember, this is the real nature of science, where you connect lots of different fields instead of just focusing on one.
Yeah, because there are multiple models. Maybe there may be other models that explain, say, general relativity, but then it doesn't explain electromagnetism, or maybe there's a model that explains special relativity, but it doesn't explain spin 1/2. It has to work for all these things, right?
Yes.
That's the big challenge. Like that's really, really hard. So okay, totally straight change of topics, and okay. Elastic. So now we have been talking about this elastic solid. Let's dive into a bit more what we mean by that. So just a simple animation of some expanding and contracting motion, right? So we have this elastic solid, and to do calculations with it, we create like a grid on top of it, like you do in a computer simulation, right? You need to have some kind of coordinate system just so you can do calculations, right? And so what we call this normally we call this a displacement field. Often, usually people use U for this. That means where there, so you have like the ground state where nothing everything is at rest. But when you have this, here you have this expansion and contraction. In the middle, there's more displacement than at the outside here, right? So you have at each point in this elastic solid, you have some number that says, well, how much, or actually it's a vector field, right? How much displacement you have at a certain point and a certain time. Similarly, we can think, the next concept would be the velocity vector field. So we can also look at, well, how fast are these grid points moving and wobbling and oscillating, right? So again, here in the middle, you see that these points are moving faster than towards here on the outside. So this also, you can visualize this as a vector field now. I think you probably know where I'm going with this. So just to make it clear, they're different in an elastic, and of course many people don't think about elastic solids a lot. So, but in elastic solids you have different kinds of waves. You have compression waves. So this is sort of the expansion, like you squeeze a rubber ball and it goes back, expansion and contraction. Then we also have rotational waves. You have a curl, a twist. It could be an oscillation movement. And let's see. Yeah, and so we can, and this is all like known physics from elastic solids that are well studied, right, in material physics. There's nothing novel about this. It's just, we can describe the wave equation in an ideal elastic solid. And basically, what it means, like on the left side here, we have the acceleration of, and again, this is the individual grid points, right? So you can imagine an accelerated grid point, and then is equals to the gradient of compression. So how much compression do you have? What's the gradient of that compression? Plus the twist of the twist. So how much twist there is. So here in this image, for instance, imagine this is an elastic solid, and we have in one place a real bulge. So we stretch it a lot, right? We have real extreme stretch. You can imagine this will accelerate. This wants to go back, so it will accelerate much faster down here than at the outside here, because here it's almost at rest. So this is very simple, like a trampoline. Also, if you just look at one plane, right, you can understand that when you have more compression or more twist, it wants to spring back quicker, right? That's just the normal, simple wave equation.
So here's my understanding of what I'm seeing. On the left side, well, let's do the right side of the equation. On the right side of the equation, we have two terms. The first term is telling us the linear displacement. It's telling us how far away from its natural position a given piece of the ether is. The second term tells us a sort of rotational displacement. It's how far is the ether from, it's a displacement. How far away from its natural position is the is that bit of ether?
Exactly.
And then well, first we're talking about a displacement. Like once it's out of place, it will then accelerate as a result of being out of place. And that's the term on the left. And this creates this gyrating motion. And since there's no friction of ether upon ether, apparently, it simply gyrates forever.
Exactly.
Or there's a conservation of gyration. It's those gyrations are only ever distributed to different parts of the ether. The gyrations never dissipate.
Yes, exactly. So and this is also very simple. Helmholtz has shown that you can, when you have vector fields like this, you can separate the compression part, so the irrotational part, from the twist. You can study them separately, so you don't always have to worry about everything mixed up, which is kind of nice. Makes it easier.
It's one standard by which you can analyze. There's other standards probably, but this is one of the more...
This helps to make the math easier, so let's just look at this part and let's just look at this part, And so the funny thing is, Maxwell, okay, he also had some kind of ether. What's kind of weird, though, because I think he was... his model, and the thing is, he derived his model based on an ether, which I think is so cool, right? Even though mainstream claims there is no ether, but he derived it using an ether. But there, it's really mechanical. He had these wheels rotating, and of course, this was kind of complex. Like, what are these wheels? What are these little balls and all that? But the idea is still, he did assume there must be something there in the universe, something that is rotating. So he was thinking that the magnetic field has to do something with rotation, right? So now when we think about that, what we just talked about, so the question then is, what is the electromagnetic potential in this elastic solid? So we have talked about the Helmholtz decomposition. So let's just look at the transverse part right now. We just forget about the longitudinal for a moment. We can just focus on that part. Now, here's an example of a motion that's just transverse. It's actually spin 1/2, but I'll show that later. Anyway, you can see how these grid points here kind of wobble around in a circular fashion, right? And now let's look at what happens to one particular grid point in terms of the velocity field, and how do we get E and B out of this? So one definition, one kind of... so when we want to define the electromagnetic potential, let's define it as the velocity, so the derivative of time, the displacement. So we call it. So the A is basically the velocity field. This is what we define, and we'll see what comes out of this. So when we do that, so the electromagnetic potential is the velocity field. So here's an example. It's similar to that wobble motion. So imagine you have on your desk a big pudding, and you just wobble a little bit. So it goes, it doesn't rotate, okay? It doesn't, it stays there on your table. You wobble it, and you place a Smartie inside. You will see that little Smartie going around in a circle, right? Can you imagine that?
What I like to say is it does a hula dancer motion.
Yeah, hula dancer. Good. Yeah, perfect. That's good. I should put it on the screen. Hula dancer. Perfect. That's exactly what it is. Yeah. So now let's look at our definition. Okay, we are saying A is the velocity field. So here we can draw the arrow, the velocity, and we are saying in this case, when we define it that way, right, the magnetic field is the curl of this, and you can see when we do this, we get a B that's going upwards. So in this model, in the elastic solid, B is basically the curl, the twist, the angular momentum density, the vorticity of velocity. So whenever you have the grid points going around in a hula motion, the hula, then you have a B field. That's pretty simple, right? I mean, that's, isn't that? I mean, come on, God. This is, and if you keep that in mind later on, spin is actually related to that, because as a sneak peek, spin is the origin, spin 1/2. Spin 1/2 is the origin of the magnetic field. So this is not yet the spin 1/2. It's just a hula hoop. But spin 1/2 is related to that, because again, we need to have something that goes in a circle to get the B field, right? So then what's E? And that was actually a little harder because so the electric field has actually two parts, and most people in mainstream, I think, ignore this first term here. It has two parts. It's composed of a scalar, the scalar field, and it's also related to acceleration. So this would be, since A is velocity, this would be acceleration. And this one is related to the amount of vibrational energy. Okay, we have to take this apart a little bit. So what is that? So if you look at this pudding here, this hula hoop, right? In the middle, here, we have more motion. So it's the stuff, the Smarties are moving around more than they are on the out far away, okay? So in the middle, we have more of this vibrational energy, right, than at the outside. And we define E as the gradient of this. So the gradient, well, how much do we go from lots of wobble to less wobble? Can you imagine that?
Yeah, so we have more wobble on the inside and less
Yep.
on the outside.
That's the gradient, and that's what we call E. That's E.
Okay.
So it points downhill from high energy towards lower energy areas.
Wow. Okay. So, and this is incredible because there's a few. So okay. This is incredible. Because I'm starting to see more connections than I had in the past.
Yeah.
There's so now. Oh well. Let me first ask this because I'm a little skeptical actually. Why is it that now E? What is E? E is a particular attractive and repulsive force among charged objects. Why is it that why would a gradient of hula motion create forces between the hula motioning things?
Excellent question. I have some slides on that too.
Good.
So basically, both positive and negative charge would have this gradient. So that question is, why would they even attract or repel? The thing is, because in charge we also have to have an additional motion, a slight circular motion that's either left or right. And so when they are both the same direction, they would repel each other because the circular motions add up. And when they're opposite, they cancel, and that's what you get the traction. Because when you have a charge, right, and you draw these arrows, the E, what they actually mean is what force a test charge would feel if you placed it there.
Yep.
Right? That's the definition of that E. And so the two directions you get from the it's a topological, the plus and minus is just topology, basically. How these waves oscillate in detail. This is just very crude wobble motion, but in charge you would have additional tiny motions this way or that way, little circular motions wobble. I have a picture later on. So a radial wobble motion, left or right, and so you get plus and minus that way.
Okay, so let's take my right and left hands. My right hand would be like a positive charge, and my left hand would be like a negative charge, right? Because they spin in opposite directions. And so let's say they're just right next to one another, and they spin like this. So they're
it's this way and that way. So you would have.
Well, okay, but if they were like this, they'd enforce one another. If they were like this, they'd enforce one another. No matter how you slice it, their velocity of rotation enforces one another. Now, why does that lead to a repulsion? If anything, I would imagine it would lead to a attraction. Oh, wait, well, it's supposed to lead to an attraction. Oops, I almost forgot that opposites attract. So is it like a Bernoulli force, basically? Because the velocity went up in the in-between area, so the pressure here is now lower because the velocity is higher, and now they get sucked together? Is it like a Bernoulli thing?
I'll show you in slides.
Okay, you're getting there.
Because it's easier if I show you with the slides.
Okay.
So basically, once we have that, we can, and I won't go into detail, but we can derive. These things are all easy to derive. There's just standard. It all works out, and it's just the only thing we have to figure out is the definition of what it means by what is the meaning of B, what's the meaning of E. But you can easily verify this works out. All the equations work out. So basically, the charge density then is the local imbalance of the vibrational energy. So it's the gradient of that, right? So yeah, is that okay? And then maybe move on to the next topic about spin and magnetism, and then we'll talk about how we get attraction and repulsion. So we get that.
If you think that's the best order, let's do it.
I don't know.
It's your presentation. Do it the way that feels comfortable to you.
Okay, so now we have covered that. Now, remember before I've mentioned that the magnetic field, right? The magnetic field is related to this hula hoop motion, right? Mm-hmm. So now spin 1/2 has always puzzled me for a long time because people don't really nobody or hardly anyone can explain spin 1/2.
Yeah.
It's literally all. If you guys understand this, you're among the few people in the world. Okay, so literally, now it's a bit hard. You have to put a lot of things in your head because it has some weird properties, right? Protons, neutrons, and electrons have this spin 1/2. It's the source of magnetism, so that tells us there's got to be some hula hoop involved here, right? Now the weird thing is, an electron has to, in quote, I'm saying this in quote, rotate in quotes, 720 degrees, so twice before it gets back to its original, which sounds really strange because so normally when you have an object, right, you turn it 360 degrees, it's back where it was. So it intuitively makes zero sense to say you have to rotate it. Right? It makes absolutely no sense. So that's why I was really intrigued by this, because we're gonna have to explain this in the elastic solid, or else it fails. Okay, if we cannot explain it, that's it. We're done. So the question then is, how can you imagine we are the elastic solid? We are inside the elastic solid. My arm is part of the elastic solid. The challenge is now, how can we do something that this thing here, this cup, whatever it is, it appears to rotate, okay, continuously. We can't spin it around. We can't flip it. We can't break the elastic solid, meaning we can't just switch hands, or we don't want to break our arm. It's this whole elastic solid stays continuous. We can't let go because it's stuck in there, right? We are in the elastic solid. We can't turn our body either because we don't actually. So how can you do this while at the same time you get back to the same place after 2 rounds? So just think about it for a moment. Do you know?
You've shown me this once before, and I'm using my little hand strengthener to see what you're show us though.
Okay, I hope you can.
I'm starting to get this a lot better than I did the first time you told me.
Okay, it's called wind dance or belt trick. So let's start to rotate my arm, and I'm basically okay. Now I've gone around once. My handle, I've gone around once, and you can clearly see I'm not back to my original configuration yet. Now I gotta do this, and I'm not cheating, okay? So and now I'm back, but see, I had to go around twice for my arms to get back to this position. So, and after a while, you get the hang of it.
Yeah, this 720 rotational property, the thing that really got it to click for me is that it's not a property of the object alone. Because if it were a property of the object alone, it would just be 360. Rather, it's a property of the object, related to the rest of the medium. It's a property of the relationship between the object and the medium.
You could attach this anywhere in the living room, and it will work. It will never tangle up. It will not tangle up, which is cool, right? Because in it, and you can tell. So imagine if you took a really heavy bowling ball here. It has angular momentum. That's the other thing which I forgot to mention on this slide. So spin 1/2 is the origin of the intrinsic angular momentum. So there is literally something going around, but it's intrinsic, meaning it's not the electron that's spinning. It's not the orbital. It's not the electron orbital. It's the intrinsic, meaning it's part of the medium itself. So that it's the medium that is doing that. The grid points.
Well, I mean, do you agree with this? It's not just the cup. It's not just the particle. It's not just the medium. It's the relationship between the particle and the medium.
Oh, totally, exactly. That's what it is. Yes. And so I have lots of simulations. I might not show all of them, and there's links. I have some simulations in JavaScript and in C# and all these different where you can play with this. There's different versions of this. This is like here, these rubber bands are like my arm. And just to be clear, the sphere is only to show where the center is. There's no sphere, obviously, right? There's no sphere. So here
isn't there, I mean, there's a sphere in a sense because there are different parts of the ether hula hooping in different ways, hula dancing in different ways. And so the sphere might represent a a surface along which we get equal amounts of hula dancing?
Exactly.
Okay.
Yeah, that's a very good way to see this. So, and also, see, I have, I don't know if you see, if you see
An
these
equa
red
hula
points.
dancing surface.
This is really good way to explain this. Yeah. So I've marked some points on here, like these red points, tracking these individual grid points as they go along, and you can see they track circles. Right? So that's basically how you get the magnetic field. And so here I have this. It's the same. This is actually exactly the same simulation, except I added more grid points. Of course, you can't see the inside. You have this whole thing here. If you zoom in, you would see that whole thing. When you zoom out, it looks like a procession, like this hula motion.
Yeah. Wow.
It's pretty simple now, right? When you think about that, and you all these circular the circles, you get the B field. It's 720
Each of the
degrees.
actual ether parts is doing circular motion, which is what would account for the intrinsic angular momentum.
Yeah,
of
you
a
get the angular
particle.
momentum, even though nothing is really rotating. So that's the confusion.
Right, which is
Nothing-
what the physicists are telling us, is there's no actual particle spinning, which then people are just like, well, what the... I tell my
what?
students that, and they just are just like, they just say like, no, that's BS. But there's a way to get that to make sense, and you've found it.
And the funny
That's
thing
amazing.
is, so if you took this cup, let's say if this was a cello pudding, you stuck it in there, okay, in the middle, and you watch, if you put it right in the center, it would actually turn around. It would turn around like this. It would. It would turn around, okay? That's what we did with the cup, right? The cup is, the innermost part is in fact rotating in circles. It's a winding and a winding, but it looks like it's rotating, so we have the angular momentum. Yeah.
I'd have to think about that more.
Okay. Yeah, actually,
And,
since we're talking about this, I also have a JavaScript simulation that I can share. I'll send you the link as well. I think I sent it in the email. Here you have actually quite a few things you can do. You can, first of all, the thing is you can rotate. You can, rotate this in any way. You can watch how these grid points are moving. You can zoom in and out. You can also, basically increase, because this is basically elastic solid, right? But it's kind of hard to see, of course, if you look at the whole thing at once. Right? Yeah. So it helps to just reduce it to look at one slice of it, right? So you can see, and then you can also track the individual motion of these grid points.
Yeah.
Right, and you can, change the speed and all that. You can also change how much this whole thing is wound up. I won't go into much detail, but also there are other simulations here. The electron orbital wave functions are here as well. You can play with all that. You can also, put in all the N, L, and M values to visualize this. Then, I have simulations
So
for
I
charge.
think I've just learned something here. What you're showing me is like, I don't know, it looks like L equals 2 for the hydrogen orbital, something like that.
Yeah, I think N is 3, L is
Okay.
1, and M is 1 here.
Okay. I didn't know, in time I learned something about the basic Schrodinger equation here. In time evolution, this is what it looks like.
I guess so, yeah.
Okay, I see, because all you did here is plug in the Schrodinger equation. Is that what you're showing us?
Yeah,
or-
I implemented all, and you can put in all the values. I also have the magnetic vector harmonics and the magnetic vector harmonics. Yeah.
Mm-hmm.
This gets a bit complicated because I have a
Yeah.
slice because there's a lot of computations and the computer can't really handle it that well. But you can visualize all these things. Yeah. And
Holy moly.
Yeah. And here I also have simulations of charge, by the way, which I haven't really brought up yet. But here is the idea of charge. It's kind of hard to visualize. That's why I added these cables in a way, because each grid point makes a slight circular motion. And there's a gradient here. And so basically if you have plus and minus charge, so when you have two charges, we can actually add a second charge. We can, and all it does, we add up the waves, right? The waves are added up. and that's the resulting. You can see the repulsion right there, right? So here we just added the second wave in the scene, and it just adds up all the amplitudes and everything, and that's what it looks like. So
I have a question about spin generally. Do you have a way of understanding the non-commuting nature of spin for its different directions? You know how like the quantity of angular momentum I don't know how to say this without using the kind of BS mathematical language of quantum mechanics, so I'm just going to use that because I don't know what else to say. The angular momentum in the x direction doesn't commute with the angular momentum in the y direction. Do you have a way of account? And that's weird, right? Like, that's weird. Yeah. I don't know what's going on there. My best guess is simply that a Stern-Gerlach magnet doesn't really measure what's going on. It affects what's going on in some kind of way we do not understand. And as a result, we always get up or down spin measurements along the direction of measurement. So something very odd is going on there. Do you have an account of what's going on?
Well, I haven't thought about this in detail right now, but basically when you have this magnet, right, there's a magnetic field there, right? Huh? So as the electron, whatever, is flying through, or whatever it is that's flying through the apparatus, there is already a magnetic field. Meaning there is already this motion, this wobble motion in there, right? That's why we have this magnetic field. So as the particle when it enters this field, it has its own spin, which has this wobble motion. Well, it's gonna orient itself, right? It's not just gonna fly through. Obviously, it's impacted by this. As it's flying through, it's affected by that field that's there. So it's going to orient itself. Or
disorient itself. It
exactly.
It will orient itself in opposition to that field, apparently.
If you just look at this as, trying to minimize strain and stress, if you look at the wave equation, right, it's always, you get the acceleration where in the opposite direction, so you minimize compression, you minimize strain and stress, so it's going to try to find the energy optimum, right? It's going away from more stress and more strain. That's just the normal wave equation.
Okay, that's vaguely making sense to me. It's basically you get less clashing hula dancing when it either orients or anti-orients to its environment.
Yeah, something like that. I mean, I haven't thought about detail, but that would be a good simulation, Maybe we should, that would be a nice computer simulation to actually simulate the magnetic field, and then simulating how this spinner is going through to see, simulate in the computer, right? What happens step by step? What would, which way would it go? I mean, that would be actually nice. I think that should be doable. That could be a nice little project.
That would be incredible. If in general you were able to describe what is today called quantum behavior, the very strange probabilistic behavior we see with quote-unquote wave collapse and those kinds of behaviors, if you were able to explain that in terms of an elastic model, I think we would be very close to a breakthrough in my judgment of staring at this stuff and being confused for 15 years now.
Exactly.
Yeah.
So, and also the thing is, there's the source code. So if anyone likes to program, you can take it, you have the source code if you want to modify the simulation and all that. It's actually pretty simple. So anyway, just see where we were. That was that. So we have the magnetic field. So now let's see. Yeah, what I was doing here, I was basically, because all these grid points, when you watch them, they make these circular motions, right? So you can now draw the B field. You can now draw the magnetic field, basically just looking every time you have a circle, right? Every time you have, because it's the curl of the velocity field, you can draw the magnetic lines. And now it's interesting when you place 2, what you can see. So what I did here, I flipped it on the side. The wobble motion, we had the hula. Now the hula is upside down, right? Like this. Rolling motion. So we have 2 hulas upside down in a way that they align with each other, okay? And you can see they are actually, when you just do a simple simulation where you, like I was saying with the wave equation, you just, let it go, basically, what happens is that you see that these the magnetic field lines align, because we have the North Pole here, right, and the South Pole on this side, and you get attraction. And when you flip it around, you automatically get the opposite, because here, the thing is, here you have circles going in one way and circles in the other, and it's not compatible. It won't, it's not going to work, right? You get repulsion. So I think that's also I think it is a movie.
Yeah, I mean, this seems a lot like. Now, why exactly do we get repulsion? Because now, I'm accustomed to thinking about Maxwell's model, where you get repulsion because the ether bits in between the two magnets do not spin as much, and therefore they do not flatten as much as the ether bits on either side of the particles, and therefore the particles are drawn together. Well, actually, that's the opposite of what would happen here. So here, so it goes like that, and it goes like this. Yeah, so the ether bits on the inside are not smashed as much. The ether bits on the outside are smashed more, and so there's more room on the outside than on the inside, and so the particles are drawn apart. That's how it works with Maxwell's model. How does it work in your model? Is it the same or different?
I don't know exactly. I have to think about what you said. But basically, it's just when you look at... it's kind of hard, because when you try to... Imagine you're trying to... you're in this elastic solid, right? On the one side, you move your whatever it is, your hand in one direction, and then from the other side in the other. That doesn't work, right? You can't.
Yeah, because you don't have two right hands.
I mean, you get too much strain. You get more strain. That doesn't work.
Oh, wait.
Right?
Oh, okay. Wait, I'm not understanding you. Say that again.
You want to, when you have a motion in this way, let's say this orientation, and then at the same time in the other rotation, that doesn't work. You will get too much strain in the system. That won't work, right?
Okay.
It's got to be. If it's going the same way, you can do it. Like you can do the wobble. If my hand is going this direction, but the other hand also, that works fine. You can do this easily in this pudding. Works fine. But when you try to do the opposite, you're gonna rip it apart, right?
Yep.
You're gonna rip apart the pudding. That's just not. That won't work. Energetically, strain, stress. It won't. We can't break the solid, right? That's not gonna work. So that's basically. It's just mechanical. It's really just literally.
I see. On a high level, I get it. The ripping for some reason causes the ripping motion somehow causes repulsion, but I would like to know precisely why, in terms of the cause and effect, the micro cause and effect relationships, it causes repulsion, and that's something I'll.
We could do more simulations. Probably we'll need to do more simulations to see to actually do it, like a starting position, right? You have these two spinners, and then just watch it, let it go, right? And watch it. So it will take, that's another thing.
That's something I'm going to think about as I continue to look at.
Yeah. Of course, with simulations, you have to be careful with numerical instabilities and all that. That's always a bit the challenge, right? So, and also in a simulation, you have an end. Your elastic solid, stop. It's the boundary conditions. That makes it a bit challenging sometimes, but but definitely, I think that would be nice to do more, actually simulate it to see exactly. That's what I have on magnetism. Now, charge is not finished. I'm working on this still, but basically, if you look, and there's different solutions. So for charge, there are different possibilities. Okay, because when we look at the definition now. When you look at the Gauss law, for instance, the charge density, right, is the local imbalance of vibrational energy. So we have something that has, in the center, you have more vibrational energy, and then you have the gradient of that. Now, we need to have two types, right? We need to have plus charge and minus charge, right? We need to have two equal charges repel, and two opposite have to attract. So the question is, how can we model that mechanically? And so far, I have seen there might be more solutions. Okay, this is just work in progress. So there's two possible solutions that satisfy that, because it has to be spherically symmetrical. and it has to have all these properties, right? You need to have two plus and minus. So maybe it's easiest if I show it with the simulation. Where is it? Simulation? Did I close it? Oh, there it is. Okay, so if we go to the longitudinal version. So one possibility, in theory, to make it spherical, and there are some people who actually use this model as the model of charge. I'm not convinced it's the right model, though. A simple solution is we have a standing wave, a spherical symmetrical standing wave, a pulsating motion like this. Let's see, I can also make it thicker. Let's see the slice. So I don't know if you can imagine this, right? It's a pulsating movement going like this. Mm-hmm. It has to be a standing wave because we know that charge doesn't lose energy, right? The electron, there's no wave that's outgoing, right? The wave stays in place. It's got to be a standing wave. Otherwise, if you had a wave that's moving outwards or inwards, and some people have this model, I don't remember who exactly, but I know some people have a model where they say, well, charge, it's like this, but the wave is either outgoing, they call it plus, and when it's incoming, it's minus, for instance, right? The problem is when you do that, you're losing energy. When you have traveling wave, you lose energy. And we know that's not the case.
Yep.
So one solution to account for that is to have a standing wave, right? So then the question is, how do we get plus and minus? Well, in this case, it would be a phase shift. So imagine we had a second one, a charge. I think I can add another one. I hope my computer can handle it. Yeah, it's a bit slow.
Well, slow is good, so we can follow it.
Well, but it's too slow to see.
Maybe not that slow.
Okay, imagine if you had a second standing wave right next to it that oscillates in the exact same way. Mm-hmm. You would get repulsion if they're going the same way. So you have the one expansion from the one charge and the other one from the other. If they keep bumping into each other, there would be a repulsion, right? Now imagine you had a phase shift of half a wavelength, right? Then you would have one charge goes this way, pulsating this way, the other one also goes this way. Then that would be attraction. It would be energetically, it's fine. You can do that. Like if you simulate this, you would get attraction, and it's actually not that hard to simulate this.
So positive and negative charge are the result of, in this hypothesis, they're a result of the relative timing of the standing waves emitted by the particle.
But that's also the problem because like that would mean they have to stay synchronous for their whole lifetime, which is kind of, I don't think that will work out, right? Because when you have a moving charge, in a gravitational field and Doppler effect, then wouldn't you lose that synchronization? And we don't see charge
from the
flipping.
Source. You'd lose. Oh, wouldn't you lose? Yeah, you'd lose the synchronization.
Right?
Through propagation. Yeah.
I think so.
Right.
I'm not 100% certain, but just because I think
it
that's
certainly
a problem.
seems like it.
So then the question is there another way to do this?
Yeah.
Because that seems too sensitive, and we know electrons are stable, so we don't see them flipping or suddenly plus or something, right? The other one is, instead of having and it's kind of hard to see, instead of having this longitudinal pulsating wave, how about we change it to a radial wobble motion? Now there is one drawback here. The drawback here is, so the nice thing about this is you get plus and minus. That's easy. And I have another simulation that shows it better, I think. Let's see if this one, I have to go to, by the way, I have a lot of simulations on this. If you go to like the collections, let's see. Oh, it's fine. I can show the screenshot. It's fine too. So these are the two models. So yeah, here the phase shift is the problem because how do we, and also traditionally, right, electromagnetic waves are transverse, not longitudinal. So that's like I don't know. the other option is to have a transverse radial oscillation that's symmetrical. The question is such a wave stable? I don't know that, right? And so it gets complicated. There could be other not, like so far we have assumed everything is linear, but there could be non-linear effects, and it's just hard, to actually come up with some solutions like this. So this probably takes some more work. But that's intuitively that's the other option, that where you have the topology is basically the charge. The type of charge is based in the topology of that motion, because you can have in the direction of the wobble motion. I'm not sure if it's easy to see. It's kind of hard to see, though.
Yeah, it is.
That's so I don't know how it can make it easier. So maybe if let's say if I zoom in, if it's easy to see, basically each grid point is making very small circular motions like this, like you see that sort of the cable structure, right? I added this to help visualization, so you can see the orientation of that. So each grid point makes these circular small. See here you can see it. See that circle there? It makes a small circular motion, and the orientation of that circle would be the type of charge, plus or minus. So when you have if this is positive charge, then the negative charge would basically, the motion will go the other direction. So if you do minus now, so I do minus charge, it's the same way, but I don't know if you can see it, but the grid points move in the other direction, basically.
Well, I have a question here. So if the direction of circular motion determines the charge, wouldn't that mean that, like, if you looked at the charge from below, it would suddenly become the opposite charge? Like, it depends. Wouldn't that?
Yeah, that's a good question. So in spin, that's what happens, right? But in charge, it's spherically it's symmetrical. So when you look out from all sides, it's always the same direction. Now this creates sort of the so-called hairball or the hairy ball problem. There is a point on the sphere where it doesn't add up. So it's not perfectly spherically symmetrical. There's a small asymmetry. And the question is, and people have tried to measure that, right? If the electron has this slight asymmetry. And so the question, this is an experiment that would actually determine that. Once we have better resolutions, that's one of the experiments that could show us, is the electron really perfectly symmetrical, or is there a very slight asymmetry? Is there an electric dipole moment, a very small one? And it has been measured down to some accuracy. So I don't know, that's the question, that's an open question, I guess, right? At some point, we should be able to determine that, if that model is possible or not, basically.
Wow, okay.
But that's good, right? So at least we have some experiments. And you asked about experiments, too. How could we determine that, right? Yeah. So, yeah, this is basically the frontier. So more work is needed to figure out some of these questions. I think this one is right now is better because it doesn't depend on the phase shifts, because that I think is a problem. And there are other people actually. So by the way, I don't want to take credit for all of this, right? There's lots of people like Robbert Close, Mark Danielewski, Ilya Schmelzer, Donald Chang. There are lots of people who have been working on this. Also, John Mackin, right? Different people have different versions of this, different aspects. Like some people have more of the topological model. Others think, no, it's longitudinal. I'm not sure yet which one is the right way to go, because I think both have some challenges, and we'll have to just continue to research and come up with experiments. And maybe there's also non-linear effects, which it's hard to come up with solutions, right? So.
Yeah. Wow. Okay. Let's see. Were there other parts of the hypothesis you wanted to share with us, or
No.
should I dive into my questions?
Yeah, I think the only thing I don't have any slides on that. Let's see, which ones did we leave out? Well, in the wave particle duality, the answer here, everything is a wave. And so the question is, I don't have a slide on that though. Photons, right? What are photons? And my short answer would be that photons are an interaction between the electromagnetic wave and whatever detector. A detector is often an electron, right? And so that interaction is quantized. It's not the wave that's quantized. It's because the only time you actually get a signal, like a ping in a detector, right, is when you are able to, when there's a wave interacts with the electron and, for instance, moves the electron to a higher energy state, that interaction is quantized. So that's why we call what we call a photon. Of course, because we can't actually see photons, what we can do is when we measure them, we see, there was a detection, and so we call that a photon. And a lot of these things can be explained. This wave-particle duality, I think, is really just the effect of detection. And emission as well is quantized, because how do you get a photon, right? You get a photon, for instance, when an electron, the energy level of the electron moves down, and that's because the electron orbitals, the spherical harmonics is quantized. You can't get half a wave, for instance. So the emission itself is quantized. It's not the wave, but the emission, you need a certain frequency for it to get an emission. So that's... and I'll probably do some slides on that at some point.
No, I have a bit of I see what you're saying. Mm-hmm. But if we follow your logic, I think another possibility avails itself, which is, again, you're saying there are no actual particles, there is no actual quantization of energy inherent in the electromagnetic wave.
Yes.
Rather, the electromagnetic wave hits some other thing that's made of waves, and for some reason the relationship between those two things is quantized. And as a result, we end up talking about photons, we end up talking about discrete energy level, discrete energies, we get things like the photoelectric effect, where it seems like the energy is received in, individual packets. Okay, I'm on board with that as a hypothesis. Let us carry that hypothesis further, though. If you were to apply that to the... Now, what you say is you say, oh, well, this quantization seems to also exist at the point of emission. Maybe, but think about this. How, on what basis what's the reason we think quantization applies, at the level of emission? It's because of what we measured from the emissions. That's number one. And then it's because of, now here's number two, and this is where, number two, it's because of the solutions to the Schrodinger equation for these emitters. For example, the hydrogen atom has particular energy levels. And what's why is it that it's quantized?
I wish I had a picture, but I hope I can draw it in the air. So basically, imagine when a wave's going around in a circle, right? You imagine a certain wavelength. You cannot, you have to have, if you have a certain wavelength, some frequency, some wavelength, right? Let's say 500 nanometers, whatever it is, right? You can't connect the wave if you do half a wavelength. You gotta have a full wavelength, so
there's
that's
a three-dimensional resonance of the wave around the hydrogen atom.
There are some pictures online with the nice electron orbitals. So you can't do half a wave, like a string when you have a violin string, or a cello. I think you've played cello, right?
Yeah.
If you imagine the string, how it's vibrating, the bass wavelength. The next one is when you have a point in the middle and it goes like this, right? You can't place it anywhere, right? It's got to add up. The wave's got to end up at the end. And when you turn it into a circle or actually spherical, it's got to make, the spherical harmonics is what is the cause of that quantization. And also, so it depends how the light is emitted. Light could be emitted in multiple ways. If it's coming from an electron, from these energy levels, then we have to look at the spherical harmonics, and that's where you see the quantization. But you can also accelerate a charge. So like a radio. So an accelerating charge also generates electromagnetic wave. And there, I see no reason why it would be quantized. If you have electrons moving up and down in a wire, I see no reason why that would be quantized. You can move it a little more, a little less. there's no reason. So I think radio waves are probably not. I mean, I don't see a reason why radio would be quantized.
So perhaps, this is the image that comes to my mind. Perhaps all of quantization is not a result of emission per se. It's a result of detection. Why? Well, because detectors are made of these microscopic ether cellos, and they can only absorb and emit particular frequencies.
Exactly.
And that's the quantization of the absorption. Now, sometimes you might get quantization of emissions, such as what you get from an atom, but you don't always, as you just pointed out. If you just shake a charge using that, the device that Hertz did to first discover the electromagnetic, you can get whatever frequency you want. It's not.
I think so.
Yeah, I think so. Yeah, that's illuminating. And as I mentioned earlier, the quantization, if you will, of spin measurements, the fact that you only ever get particular discrete values for your spin measurements in quotes, because I'm not convinced it's really a measurement. Perhaps that is a similar, quantization of absorption effect somehow.
I'll look into that too, and I'll think of doing a simulation. Maybe that would be interesting. Yeah.
Because to me, in my view, I need to spend more time thinking about this, but based on my cursory overview, an understanding of quantum phenomena, of specifically the discreteness of absorption and the apparent randomness or like the current randomness that we have in the measurements, and what is the phenomena surrounding what's called wave collapse. This is the thing that I've never seen an ether model fully account for. And so I think if you could account for it, while accounting for all these other puzzle pieces you've shown us at the same time, that because as far as I'm concerned, it's already plausible with all these other puzzle pieces. This fits together, at least on the surface level, from what I've seen so far. It fits together way better than anything I've seen from anyone else. It's that one piece, so if you were to get that one last piece, it would be incredible. It's already incredible.
No, actually, this has been published. I mean, it's a guy, I can't. Sergei Rashikovsky, can't say his name.
Okay.
I need to extract. I need to make it into something that's readable and presentable. It's like some of these papers are really mathematical. So and I do have. I think I have some on my YouTube channel. I have some podcasts. AI podcasts, which take papers and they discuss the paper, which is kind of fun. I do
cool.
I don't know if you've seen it, Notebook LM. It's pretty cool. I should send you a link. So I do have it there, but I don't have slides yet. And then maybe for the conference in Germany, maybe I'll add that. I'll try to get it done by then. It's you're gonna be there too, right?
Yep.
So I'll consider that, adding this question about that, because he has answered those questions. Both photoelectric effect, all these things related to detection and emission, and so he has addressed all that very cleanly with a pure wave model. It's just a matter of trying to explain it,
Wow. Yeah. That
he's
would be
really
incredible.
smart guy.
I really look forward to you making that easier for us, and
I hope,
in a few months I will have more time to look at. I've been neglecting your side of my endeavors because I've been focusing on my fundamental math videos, but I should have time to focus on this stuff more in the coming months. So I really look forward to that.
Yeah, and the other thing we haven't talked about is matter and antimatter. I mean, this is really kind of trivial because when you have noise-canceling headphones, it's the same concept, right? You have a wave, the mirror wave, which cancel each other. So this is really nice explanation too. This is really simple actually to understand. So for me personally, charge is the hardest one because there's still some questions about that, how exactly it works. But everything else, yeah.
Now, I still have a few questions, if you have
Okay,
the
yeah,
time.
actually I'm done. I mean, I have one more slide about, one more, just summary about, some people have like the fluid ether. I see some problems there because in a fluid ether, we know that these particles, in quote, are stable, right? When you have a fluid, how do you keep everything stable? How do you get transverse waves and all that? That's why I think a fluid ether doesn't really work. We haven't detected any ether drag or anything like that. So that's the reason why I think an elastic solid makes more sense. Then the other one I have, you asked about some ideas for experiments. So I think if there's an elastic solid, we should, at some point I hope, we should be able to measure some things, right? Because in theory, in any medium that we have, the ultra short wavelength, the speed of the waves depend a little bit on the wavelength. When you have waves that are really small and approach the resolution of the medium, so if this is granular in some way, we don't know, right? If it's granular at the Planck length or something, we should see that the gamma rays, for instance, ultra short wavelengths should be, I think, a little slower than these waves should be slower a little bit. So we should see some delay, but I think we're not there yet. I don't know. If we ever see a delay where, short wavelengths, they take longer to arrive, that would be an indication that there's this granularity. The other thing is, this one. This is a topic that could fill another 3 hours, but this is a can of worms, okay? But, imagine, like in normal media, you would expect a small energy loss over great distances because of the interaction of the wave with the medium. So photon waves would get redshifted a little bit, in theory, over great distances, which would then explain the redshift without actually expansion. So in this model, it basically means there is no expansion of the universe. The redshift is actually caused probably by a very, very small, tiny energy loss over great distances. So, and we know how this works mechanically in normal elastic solids. So if we could use that research there and do some experiments to detect that somehow in a lab, I don't know if that's possible.
It would be interesting to see if the Hubble constant is actually giving us insight into a property of the medium.
Exactly. There's all this discrepancy now in inflation and like maybe that's not correct. Maybe there is no such thing. It's just an artifact from the elastic solid, right? Could be. So
we could also delve into the research on the alleged acceleration of the expansion and identify
same thing. So
what that actually, because there's some, to me, from my brief reading of this, now it's accelerated, or the expansion's accelerating and we need to account for it with dark energy. And that sounds like a papering over of like a prior hypothesis that was never up to the task to begin with.
It sounds like epicycles to me. Like
exactly. Yeah, that's what I should have said. Exactly. Yeah, it sounds like epicycles.
Like
exactly.
I was always, hey, Big Bang, of course makes sense, but then inflation and this and that, like it's too much. Come on, it's just like epicycles.
Yeah,
that something is not adding up. Maybe we should just start again from the beginning. And what bothers me, people are not even asking the question, like. Also, we see these really old galaxies. I don't know if you saw the news, like older and older, like 300 million light years after Big Bang. How is that even possible? Because the rotation of a galaxy, of the Milky Way, one rotation is 200 million years, okay? Mm-hmm. So when you watch computer simulations of galaxy formation, there are online, you can look at these simulations. They rotate. There are many, many rotations until you get a full galaxy. So how can you get a full galaxy only 300 million years after the Big Bang if one rotation is 200 million years? That's like 1.5 rotation. Boom, it's there. It's like, come on. That doesn't add up,
Interesting.
So anyway, another puzzle piece I should have added it on there too, by the way. Yeah, the whole universe needs to be explained as well, right? So if I'm making a bold prediction here, if I had to, just based on all we know, I would say there's probably no expansion. It's the redshift is probably based on medium properties, small loss of energy somehow. and the universe is probably infinitely large. I don't know. And so if that's true, we should keep seeing older and older galaxies, right? If that's the case, there should not be an oldest. We should be able to see more and more.
Now, this gravitational refraction experiment, tell me about that, because it says it's currently feasible to do an experiment like this. Is this something where your model has a different prediction than general relativity?
I don't know if this is actually feasible. Yeah, but this is just... Yeah. No, I think if there is... if there's a smallest scale, basically, right? If there's a Planck length, maybe at some point we can, figure out some deviation of mathematically, right? Some. I mean, even the mainstream has argued there could be a smallest scale. So, I don't know. I don't think it's currently. I have to. This is a summary. I don't know if that's actually possible. I hope it will be possible.
I see. Okay.
So,
you didn't mean to mark it as feasible.
Yeah. This is not worked out in detail. Okay, I was just trying to, get some ideas. Yeah.
Preferred frame detection.
I don't know if that's possible either, right? So if there's any, people are always trying to do that, but
yeah, right.
I don't know. Anyway,
yeah,
but there's several experiments that might
of
indicate something, right? So.
Well, that is very exciting. Do you have about 20 more minutes for me to ask you some questions?
Sure. Yeah.
All right. So now here's an important sort of basic question. Do you think that this model is literally true? That the ether is literally an elastic solid?
I see why not. Yeah, I think so, because
now there's a okay.
Okay, go ahead. The option is
there's a bit of a problem there, because your claim is that matter is a particular kind of wave in the ether. So how could it then be that the ether itself is made of the stuff, is made of a solid, when solids are an emergent property of the ether? So
that's
you
a good
can't
question.
literally mean it's an elastic solid, right?
Well, not a earthly elastic solid. It's not like dirt or something. It's got to be... The elastic solid is just the vacuum itself. So basically space is something. So the word elastic solid is really describing the properties of that space, right? Or of that vacuum.
Yeah.
It's not a real
this is my
way. Substance. It's not a substance that we know. It can't be, right? It's not like a rock or something. It's the properties. So space has properties. It has, elasticity. It has... it can be denser. That's how I would describe it. Elastic solid is more like a visual thing to help imagine your pudding, right? But of course, we use words that we use in our everyday lives to describe this, even though it's not going to be material that can't be, right?
Yeah.
So basically, spells. Yeah.
My way of thinking about this is that it's not an elastic solid, but that elastic solids give us a set of physical cause and effect relationships, and the relationships between the characteristics of the ether that are known have the same relationships between one another as the relationships between the characteristics of an elastic solid.
Oh, yeah, I agree. Totally agree.
That's my way of thinking of it.
Yeah, makes sense.
Yeah, I think these questions are really important to answer on a fundamental level, because Maxwell, you mentioned Maxwell's model, and his model was insanely successful. Like, that model is what discovered electromagnetic waves.
Yeah.
He insisted that he didn't think it was literally true, and for good reason, because of this consideration. He didn't think it was literal wheels frictionally grinding against one another. But he said there must be some analogy, and he thought that the model... And I think his model has the same status, which is the physical cause and effect relationships that would exist between a bunch of gears grinding against one another in this way are the same mathematical relationships between whatever physical properties underlie the electric and magnetic fields.
Yeah, makes sense.
Yeah.
Yeah, so similarly, exactly, yeah, that makes sense.
So now you've made reference when talking about time dilation, or as I like to call it, duration dilation, you've made reference to a kind of godly clock, like a standard of time that isn't changed in the way that, durations are changed by motions through the ether.
Well, that's kind of artificial. It's just because when we talk about it, like when I talk about the simulation, I have to use some time, like in the simulation. So, and of course there, I'm not using the local time in there. I'm using this abstract outside time, which doesn't exist. This is only to help with the talking about it. So I don't think time really exists anyway in that sense. I think time is more just, there's change of some sort, and that's what we call time. I don't think time exists. You know what I mean?
Well, I would say time exists. Like, we shouldn't throw that word away.
We call
but
it
time is not like a dimension like space that we travel
exactly.
through.
It's not a dimension.
Yeah.
It's something we measure, like how long it takes for something to go in a circle or whatever, right? And it can be slower or faster, but it's not a dimension like in a spatial dimension. That's why I never really liked this Minkowski space-time, because, like, what would that even mean?
Right. I never even got that far. By the time I started hearing about more rational alternatives, I was still confused about what they were even talking about. I think thinking more about what time will be fruitful in the future. But I think the first step is definitely what you just said, that time is just something that like the way you put it, like there is no time, there's just change, is kind of I think the word time should still like reference something, but like time certainly is not this dimension that things are moving through.
Yeah, exactly.
The fact is that things are changing and interacting, and when the things interact with one another, they interact when they're in a certain state. When you and I talked, I was 36 years old. I was not 50 years old. So like I am in this state right now while receiving, actions from you. That's what time has to do with. That it doesn't have to do with like moving through something. Yeah,
exactly. And it's also when we say time goes slower, it's really my clock that's moving more slowly as I'm traveling faster. It's the clock that's moving. It's not literally time that's slowed down. It's my clock that's moving. My atoms vibrate more slowly, or all that. Everything is slowed down. It's not time itself. So it's the mechanical motion that's slowed down, basically.
Yeah, that's why I insist on calling it duration dilation instead of
that's a good idea.
Time
the time is kind of
dilation.
confusing. That's a good idea. Yeah, okay. Yeah, good.
Now let's see. Okay, let's see some of these. Okay. Let's see, how much time do we have? I'm gonna just go to this question. Yeah. So back to Maxwell, he made a similar hypothesis to this with a medium. You and I have talked about experiments, things that we might do to test this hypothesis. But I want to point something out. Maxwell's ether model was tested in a certain way. And the test was extremely successful from a certain perspective. He discovered electromagnetic waves, right? And then Hertz confirmed them. So that's incredible. That's an incredible success. But let me point out a way, I hate to call this a failure, but like a certain shortcoming. Maxwell's ether was not proven. You can think of that as a certain shortcoming, or no progress was made towards understanding the fundamental nature of the ether, except of course that there were electromagnetic waves. My point is, though, what am I trying to say? Because it's like Maxwell was successful, the end.
Yeah.
But what I'm trying to say is, you've given us a specific hypothesis about the nature of the ether. And my question is how would we prove it? And And you might say, oh, well, we test it. Okay, but let's get into the details of what that entails. Maybe it would look like this. You put all the pieces together. You put all these pieces together. And then you say, okay, because of all these puzzle pieces we see before us, the ether might be like X. It might have these properties. If it has these properties, it will then commit this extra action we haven't seen yet. Does it? Then we go out into the laboratory and we see, oh my God, yes, it does do that action.
I think
now
it's also difficult to prove something. All we can say, is it consistent? So we can say, is this model consistent with all we know so far? And we can say yes or no, right?
I think that there is an alternative scientific method that can allow us to not only test for consistency, but also allow us to prove new things beyond a shadow of the doubt. For example, the atomic theory of matter is not just consistent with chemistry. We know that atoms really exist. Even though we didn't see them or even optically image them until 2001 or something like that. Atoms were known for a long time, and it wasn't just and what I'm developing is the specifics of a different scientific method that actually allows you to prove things instead of just sort of confirm through experiment.
Great.
So this is why I asked the question: if we were to do what I just described, like come up with a novel prediction, test it, and the test came true, that would be incredible. First of all, let me just say, that would be incredible. That would be an enormous achievement. It would be exactly of the same form of as Maxwell's achievement, only on a broader level. What would it be? It would be, here's an extra phenomenon. Here's electromagnetic waves. That's what Maxwell, predicted, and then Hertz discovered. And you would achieve, and if you were to do this, you would have achieved the same thing as Maxwell. But you would not have proven the nature of the ether, just as Maxwell didn't. So I think another route... Now, that doesn't mean there's anything wrong with that plan, by the way, because you'll still have discovered something new, and it's not like Maxwell... Right. And I mean, discovering electromagnetic waves was an enormous success. But the purpose of... I guess this is more of a comment than a question. I would simply propose another route. That's one good route. Here's another one. Identify the facts. Identify all the facts of these different puzzle pieces. And instead of identifying a hypothesis which is consistent with all of these facts, you instead make deductions from these facts to identify facts, additional facts, basically.
Totally get it. Absolutely. Totally.
Now let me point out, now that I'm thinking about it, to toot my own horn a little bit, I've already done this. Not on any level that's very impressive, but I've already done it, and let me show you how. There's a video where I break down the electromagnetic wave equation and show, without any doubt, that there is an entity at each location. I make deductions. And you can watch the video to see if you agree with the deduction. I think basically, have you seen this video of mine where I
have seen it probably. Yes.
It's the one where it's the gray thumbnail where I have a magnet and I'm thinking about it.
I'll watch it again. I'll rewatch it to remember exactly what.
So I think it is very important to watch that because it demonstrates this alternative scientific method where you're not hypothesizing and confirming, but rather you're looking at the evidence and then deducing from that evidence. And when you do that, you actually gain certainty about whatever you deduced from.
Absolutely.
Now, you have to check, to be clear, you have to check the deduction in certain cases, although the deduction I made, there's nothing to be checked because the results are what they are. And basically all what I did is I showed this situation has all the properties of an entity. Therefore, there are entities here. So the reason I say this isn't that big of a deal is like we already knew there was a friggin' ether. But now, what did I do? I made it, like to toot my own horn here, I think I gave us something really important. I gave us complete certainty that there is an ether. We
That's
already knew.
awesome.
Yeah,
That's
it looks
really
a
cool.
lot like
That's
an
really
ether.
cool.
But yeah, like I think so. So that can be used as a model for another way to probe deeper into nature. Again, looking at these phenomena and then just asking, well, what can be deduced from what is known so far? And if you look at the history of science, I think that method is used much more often than the hypothetical, the hypothesis and check model. And a lot of times it's sort of a combination.
Let's brainstorm about this. Maybe in München we can put our heads together and come up with ideas,
I think that's what I'd like to do actually. Once I'm done, I'm writing a philosophy article right now, and once I'm done with that, let's do that.
Yeah, I'll definitely. I have some vacation coming up, and then I have some time to also kind of think about this,
Good.
Wow. Because of course, first we have to kind of show doesn't even make sense to go down that road, right? If you figure out like, oh, it's not compatible with say spin 1/2, there's no point, right? So, but now I think now I'm comfortable that this really fits well, that it makes sense to start to making these deductions because like before, if you're not certain, right, there's no point in spending all this time.
Yeah.
Everything fits together. I mean, that's the one model I haven't seen anything that wouldn't work basically so far. So, I think it makes sense.
It's important to note though that there's something dubious about like tweaking a hypothesis until it all fits together. That's exactly what we were criticizing the expanding universe astrophysicists for. Is they kept seeing. Of course. There's something different about that, which is they kept seeing new phenomena and they kept having to add additional hypotheses to explain each of the new phenomena. So I'd have to think about what exactly is wrong with that. That, of course, feels wrong, but I want to identify exactly philosophically why that is improper, or at least why it is very likely that your hypothesis is wrong when that starts to happen.
Yeah, like similarly, right now the elastic solid is very simple. It's all there is, elastic solid. There's nothing extra. There's no other variables. As soon as you start to add new variables, let's say we postulate at the small scale, there's also a rotating thing. Well, now that's suddenly you're adding this new concept, and that's a problem.
Yeah.
We shouldn't have to add anything to that. If it's all just the elastic solid, well, that's all it should be. We shouldn't have to invent new elements in there to explain things. So as long as we keep it that way, no extra variables, right? I think that's really important because every time you add something, you have to really, there has got to be a good reason for that. Like,
Yeah. Well, okay. This is very exciting to see where you'll take this, and I'm excited to do my part to help you.
Sure.
Any last things you want to say before we log off today?
No? Well, thank you very much. It was great talking to you. Looking forward to meeting you and brainstorming. Maybe we'll get one step further. That would be so nice.
I think we will.
Yeah, cool.
All right. Thank you very much, Chantal.
Thank you. Bye.